Sir, you are muted, sir.
Sir, your mic is off.
Yes. So now I guess I can hear you. So yeah, I mean in between, whenever you feel like there is a need for discussion, any point is not clear, feel free to interrupt me. And I will get back to the recordings as well. So I have already mentioned that in case you have any problems with the recording lectures, any point not clear, I will revisit those. But before I do that, I'm just going to give you an overview. So these are the courses that you people have done. The first row, analog circuits, digital circuits, theory and lab, signal processing, network theory. These are common to both EE and EC people. And the second row, semiconductor devices and electromagnetic engineering. That is done by EC people, not E people. But again, I will not assume that there is any significant disadvantage if you don't have the lower two courses. I will not assume any prior knowledge of the lower two topics. And you may have, upcoming semester, you will have some more important courses like control theory. You will have DSP. You will have uh, some more, I guess, communication related. EC people have more communication related courses like analog and digital communication. Uh, EE people have instrumentation related courses, machine related courses. Machine related courses are not so important, but instrumentation related courses, um, that will be important. So you're going to have some more core courses which will be helpful in your VLSI knowledge based development. So all these topics, by now you have covered, and you will see that most of the things that you've covered here will be eventually utilized in your journey of VLSI, learning, design, projects, etc. That's why this topic is so demanding, and it requires good knowledge base, not only in analog circuits, not only in digital circuits, but other aspects also, like the signal processing part, also network theory part, also. And in the form you might have seen, I had also mentioned programming and data structure. What is that course called? Is it still programming data structure or something else? That first year programming course? What is the name of that course?
Yes, sir, it's called them.
Yeah, PDS only. So in the digital design, when you go to digital, you will see that the design methodology for digital is uh, more, I would say, programming related. So there, ultimately, the digital design is done using some programming languages. Some of you might have already done it. So anybody has covered basics of HDL languages like Verilog, VHDL. Anybody has done in the courses, in the lab, anywhere so far? Anybody has covered uh, the programming languages for digital design? No. Anybody?
Very long.
Yeah, Verilog or VHDL. Anybody has done?
Sir, we had it in our digital field.
So you had in the digital theory or lab?
Theory.
This is EC people or E or EC?
E.
E,
Yeah.
which is good. It is actually useful. You should have it in the digital theory course. EC also used to have it, but later they somehow removed it. When I was there in EC department, I also tried to bring it back, but somehow it has not happened. Hopefully, it will happen, because ultimately for your uh, third year, at the end of the third year, whatever companies, etc., come for internship, they will expect that the digital part is also, at least the basics are there. You are able to code, you are familiar with some of the basic languages like Verilog, VHDL, etc. So we will try to see in the course also, because we have a whole summer here. So later part of the course, we'll try to cover some of those things also and take some sufficiently complicated examples so that all of you get some practice of this as well. So fine. Now talking about the overall, application. So VLSI as a topic, of course, it utilizes the knowledge base in all these domains. As I said, EC people may be having communication related courses coming up. All of you will be having DSP. Likewise, there may be control. So eventually, all these are going to be useful for your VLSI knowledge base, because when you are doing DSP, there are VLSI chips which do the DSP operation. Even an FPGA board will have a DSP chip. Your many different applications, many IoT devices will also require DSP chip which do the digital signal processing. Likewise, control is an integral part of analog as well as digital block. So this concept of feedback and stability, loop stability, those things you might have covered, means at least to some extent. Uh, so in the analog circuits also, the concept of feedback and stability has been covered. So there are some more advanced topics in control where we can have some techniques for compensation or stabilization of feedback loops, because feedback loops are integral part of analog circuits, and even in digital domain there are several architectures, several applications like filters. Many signal processing blocks also use feedback, and they have some control schemes involved to make those feedbacks stable. So all these topics, all this theory related to programming data structure, DSP, control, communications will come when you're talking about communication circuits, whether it is wireless communication, wireline communication. So some basic concepts of communication theory should be useful. And ultimately, people who build circuits for communication, they should be comfortable, they should be conversant with the essentials of the communication theory. So that part, although it is not covered by electrical engineering people, but in case in future any of you is going towards communication circuits, wireline communication means communication through wires, communication between chips which are sitting on the same board, or communication between two different blocks on the same chip, or wireless communication between different modules. So all these communication circuits, they may have optical communication also, like the example that I took in that transmitter receiver circuit that was having a receiver block based on the common gate circuit, and it has a photodiode. So there, ultimately, the assumption is that the communication is happening in the optical mode. So optical signal comes and it can produce a current in the photodiode, and that current can be received and amplified by the common gate circuit. So likewise, many different kind of communication circuits for optical communication, on-chip communication, off-chip communication, wireless communication, that will require some sophisticated circuits, which it's also good to have the background of communication theory, so that some of the design challenges, some of the design specifications related to those circuits are understood. But if you don't have communication course as of now, don't worry too much. If anybody wants to develop those basics, it doesn't take too much time. You can read up and you can develop. So devices part, the easy people have the advantage that they have gone through a more detailed device course. But again, we will not need all those detailed device physics. Whatever understanding of device is required, we will discuss as and when required. In this semiconductor device courses, they go a bit more detail into the device structure, the transport mechanism, the derivation of device equations, the semiconductor physics behind it, the quantum mechanics behind it. All those things are also covered. But right now, those things are not required. You need to understand the device operation, the terminal characteristics, the basic principles behind the device operation, how the small signal model comes, how does the device operate. So some of those things have been covered in my recorded lectures also that I shared with you. And that's why I say that in case you have any problem, anything is not clear, we will, discuss. So those are essential things. And in case you have any doubt in those parts, you can, definitely discuss. And as I said, as and when required, in between also, if any device aspect is not clear, any part, large signal, small signal, uh, AC analysis, DC analysis, any part not clear, you can interrupt me. Yes. So going ahead, so somebody is messaging that they are having problem in joining the session. So let's once again, I don't know. So most of the people have joined. So there is a way to pause the recording also. Wait a minute. So recording stopping is one option, but pausing was also there. This I don't see that pausing option maybe, but let's see. So there is a problem. So 4, 5 more people. I have accepted all, so I hope should be fine. Okay, so going ahead, this is recorded. So anybody by chance missing this lecture, we should have the recording also available. So I was talking about the overall uh, topics involved and the relevance of all these different uh, courses that you have taken in this course. Uh, in case of say analog and digital, so in at an early stage, many of you may have this question whether analog is more interesting or digital is more interesting, which way I should go. So it's a good idea in this age to basically be aware of the fundamentals of both, being able to do a project on both sides, because eventually, even if you are working on analog designs, if you are working on some practical analog circuits, inevitably you will find digital units in that. So, for example, if you're working on ADCs, analog to digital converter, amplifiers, regulators, so these days there are a lot of digital circuits which are also involved in analog design. They are called digitally assisted analog design. So this analog versus digital, you should not have a right now. You should not become selective. That okay, I am liking analog only. I am liking digital only. Preference is okay, but at least having the fundamentals of both and being able to use tools in both domains is important, because generally, for any practical design, both will be required, especially if you are in the analog domain. If you are purely digital, if you are, purely, working on digital domain, then you do not need so much of analog, because there are RTL engineers, digital design engineers who don't worry so much about analog, but the basics they should also know, so that when there is a time for integration of any digital block with analog. There are many circuits, many applications where a digital block will be sitting side by side with a analog block, and they will be communicating with each other. So they should be aware of the basics of analog design also. They may not go deep into the analog, they may not do the design themselves, but at least the basics they should be having. Analog, I would say, if somebody is an analog design engineer, for them knowing digital is very important, because analog, uh, most of the analog blocks, commercial analog blocks that we have today, it may require some or the other analog digital circuitry. Sometimes it may require good amount of digital support. It may have good amount of digital calibration circuit, digital support circuit. They are called digitally assisted analog design. So for an analog design engineer, it is very important that they are aware of digital concepts also, and they have to deal with the actual digital design. Many times they have to deal with the Verilog coding and generating the digital circuits themselves, combining and interfacing them with their analog block. even the signal processing part, right? So we will discuss that. We will take examples. We will see that even the signal processing part you may have to uh, be aware, because when you are developing analog circuits for a particular signal, for a particular application, you need to understand the signal. You need to design your circuit to process that signal. Therefore, analog people are relatively more, I would say, uh, more the expectation from their side in terms of knowledge base or in terms of the know-how is more, because they need to be aware of multiple things, right? So they need to be aware of the digital side, they need to be aware of the signal side, they need to be aware of they need to be more aware of the devices, because digital side people mostly deal with the digital levels, high or low. But when you're talking about analog, you have to talk about the small signal operations of the device, and a lot of other small signal parameters, noise effects, non-ideal effects in the device. They need to be aware, because analog signals, analog processing is very much sensitive to those device parameters. So they need to be more conversant with the devices, device operation, device characteristics, device non-idealities, as compared to digital. Digital people also need to be aware, but analog may need to be more, well informed about the device non-identities, especially for the advanced nodes, advanced MOSFET node that people are working today. So if you want to be analog design engineer, then you can't leave aside anything. You have to be good at digital. At least you should be able to code a digital design, a small digital block, which is going to be used in your analog design for supporting or calibration, etc. You need to be good at signal processing. At least good means you should, if given a signal for which you have to design your analog circuits, you need to know the basics of the signal. You should be able to do the basics filtering, or a Fourier transform, or analyze the signal, uh, do different kinds of processing on the signal, so that you know that when actual circuit implementation comes, what kind of circuits are required to process that signal. So at least some basic idea should be there. So in an end-to-end project, this can also be, it's not necessary that same person will work on everything, but when you are interacting with a signal processing person who is purely doing the signal processing, and you're trying to design a circuit, suppose somebody is working on a biomedical signal processing, and they come and say that, okay, we have figured out an interesting way of measuring a body signal or a heart signal and extracting some important information out of it. Can you design a chip for it? So you need to know the questions to be asked. What kind of questions you will ask? What kind of signal parameters I need to know? What are the characteristics of the signal that I need to understand, so that I can decide what kind of circuit, what kind of chip, what kind of challenges are there for that circuit to be designed, for that system to be designed. So basic ideas are important. So in terms of say, uh, in terms of the domains, so I had the discussion earlier also. So when we talk about today's application, so at the highest level, if I look at the design hierarchy, so at the highest level, we have an application, right? So we start with an application. We can have any application in mind. You can say a simple application where, let us think about an application where you are trying to say measure a seizure signal. So there is something called uh, epileptic seizure. So seizures happen in brain because of neural signals having some disorder. So that is a neural disorder, because of which the signals in the brain, they are basically having some undesirable activity, which leads to unwanted electrical signals in the brain, and it leads to seizures, physical seizure. So seizure detection. Suppose there is a application where there is a chip design for seizure detection. So what does it do? It has, say, there is a human skull. Within this, you have the brain, and the brain is made up of billions of neurons, right? So there are billions of neurons, and they are connected with each other using synapses. And the neurons have a lot of electrical activities. So they are having electrical signals small millivolts of signals being circulated among themselves. So whenever we are carrying out any mental activity, thinking, seeing, feeling, each and every small activity leads to flow of signals in this huge cluster of neurons, billions of neurons in the human brain. It's a very complicated structure. And if there is any uh, problem called seizure, there we may see some disruption in this normal activity of the neurons. What happens is in under seizure condition, some part of the brain, the neurons become synchronous. That means the electrical signal will start fluctuating in a synchronous way. Just like you might have experienced this where you have echoes, right? So when you in an online meeting, if you connect from two sources, you will start having echo, right? And it will lead to a huge beep sound coming because of oscillations going on. Your voice is coming from one end, getting recorded, transmitted. Same voice is coming from another end. So it's going in an iterative cycle. So that becomes likewise in classrooms also you might have noticed that kind of phenomena where there is a multiple mics are operating and all of a sudden you get a big beep sound. Likewise in the brain, what happens is because of all these there is some structural defect in that neural circuit at some point. Some parts of the brain, that means neurons in that region, get synchronized and they may emit a synchronized electrical signals. All of them start emitting synchronized electrical signals, uh, because of which, wait a minute. So somebody, yes, tell me, somebody is at the door. Yes, come in. This is about the course or what?
Yes.
So you have been given the, login.
Yes, sir. I just signed in to the link, but I failed to join in multiple times.
So,
The link.
so right now we talk to your friend because I cannot interrupt my.
Okay, sir. I asked you some few ones also, but they also get.
So beer for today, you fix the setup maybe after this class.
So is any
Right now, if there is a class, so after you recording will be available, you go to the recording, and then tomorrow onwards you fix this issue.
Sir, is there any official emails where it's
In that group, whatever is happening in that WhatsApp group.
ask you? Sorry, okay.
So now the seizure detection part, the motivation behind this application, which I have just taken as an example, and here the motivation is that when the seizure happens, when this synchronous activity of the neurons starts, it leads to convulsions because this amplified electrical signals, they lead to abnormal behavior in the person. They start shaking, vibrating the body very vigorously. They feel a lot of strain and pain in the body also. So that is a very abnormal activity, and it leads to a lot of physical strain, emotional strain for the person. So now to handle this, people tried to figure out ways through which they can predict the seizure onset, that even before the seizure signal starts happening and finally it blows up, can be detected in early stage so that we can do something electrically or externally to stop and further amplification and build up of seizure. So this is early stage detection, early stage detection. I'm just giving you an example of an application. So in the seizure signal, can we detect the seizure onset at an early stage? This is called the onset period. That means in the very early stage, it's something like nipping it in the bud. So when it is just starting and signals have started building up, you try to sense this, and then there are ways in which it can be controlled. Either you take a medication, or there may be possibility of stimulation, electrical stimulation, to basically cancel out or disturb that synchronous oscillation. So basically, an electrical solution to this, an electronic solution to this will be that you are having a small chip somewhere, either implanted or outside. It senses the early stage and it also stimulates. It provides some electrical pulses which can disturb the synchronous oscillation. For example, it is something like hundreds of neurons protesting, right? So they started protesting, making a lot of noise, and that noise is starting to build up. But now this is having a police control. It is detecting that buildup. Now these people, these protesters are coming and they are going to create a lot of noise. The police is detecting it at an early stage. And then they start a lathi charge, right? They have a lathi charge and they provide electrical stimulus so that that crowd scatters, something like that. So here, this chip is supposed to detect that onset of that protest. This signal is building up, they detect it early on, and then they start the lathi charge. That means electrical stimulus, external electrical stimulus given to this region of the brain so that that buildup is scattered. And then that, this region is prevented. That is something which people have proposed earlier in literature, and this closed loop operation, detecting and stimulation, has been tried by some researchers. Now, this idea, first thing is, this idea is coming from the biomedical domain, medical domain. So people might have carried out experiments with rats and monkeys and rabbits and so many other animals and tried to basically uh, understand that how this can be controlled. So maybe they carried out some experiments with the animals. They, whenever the seizure is happening, they try to inject those electrical pulses to disturb the seizure signal so that it can be stemmed, it can be controlled, it can be brought down. And then they came to an engineer, electronics engineer, that, hey, means I have discovered a mechanism through which I can control the seizure. I can, uh, detect the seizure early on and suppress its further amplification. And that way I can help the patients of this epileptic seizure to, have a normal life. They will be free from this recurring seizure problem that they are having. So now they say that, okay, means we are doing it in the lab. We have done the experiment in the lab with humans also. Maybe we have done some experiments, or with some animals we have done the experiment, and we have demonstrated this operation that it is working. Now, how to make it available to people? I can't have people sitting in the lab all the time, right? So they are doing their normal activities. They are going all around. They are, doing their jobs. They are studying. They are traveling. So I need to have a system. I need to have a solution which will enable them to use this phenomena to suppress or mitigate the effect of seizure. So I need something which they can wear, maybe an external device, maybe some sensor and some chip which can be worn by those people, or it can be implanted within those people's skull, right? There are two kinds of biomedical devices, either wearable. That means you wear it outside the skull. Somewhere it will be sitting. Maybe it will be sitting in your eyeglasses somewhere, close to the ear, or it will be sitting somewhere. It is a wearable device. Or you are having a hairband and you are having that device sitting somewhere on the hairband. Or it may be implantable. It may be inside here. Okay? That means the operation has been done and skull has been opened, device has been inserted, and that device is operating from there. That is implantable. Of course, wearable devices are much less riskier and less, costly. Implantable is more risky and costly because it needs a surgery. You have to put the device inside, and there's a risk also. So, both methods people have tried to use for biomedical applications. Now, you say that, okay, means now an electronics engineer, VLSI engineer will say that what is the feasibility? Now, signal processing scheme is fine. Means there is a seizure signal that we have to detect, and we have to provide the stimulation. And for that, I need to design a chip. There has to be a small miniature device which can be either worn in the on the head with the help of a band or glasses or whatever, or it has to be a even smaller chip which has to go inside and sit inside the brain. And then based on the application, you have to decide how to approach, right? How to, decide about the design challenges, right? So, for example, if it is a wearable device or versus implantable device, what are the challenges? What are the big differences between these two? Anybody can say? Like in terms of the circuit designer, chip designer, what are the big difference between the two cases? Yes, anybody?
Sir, if we have a wearable device, then we have it in contact with the external environment also. So it will pick up some other type of signals also along with the main signal, like noise maybe, or due to some friction, some other signals. Whereas it is, if it is inside the brain, then that chance is less.
Okay, but that's, I would say, it's not a very big challenge. You have thought of something that, okay, if you're sitting outside, you will have some interference with outside signal. Inside, it is not so much. Uh, but I tell you, that's not a major issue because that chip is in it is in contact with the skull, and the sensors are attached to the skull, so they pick up the signals from the skull, and it is not an acoustic signal or an electromagnetic signal. It is some special kind of sensor which will detect only some special signals from the skin, from the skull. It is not going to pick up environmental noise, or basically it is not going to pick up electromagnetic radiation. So there are some special sensors which sense certain things. So that is not a major concern. Maybe a minor concern in case you have a lot of interference from other sources. Any other major concern? Any other major concern?
So the implantable device needs to be biocompatible.
Biocompatible, yes. So, that is a good observation. Biocompatible means ultimately it is going inside the brain. So it should not damage the tissues. It should not heat up the tissues. It should not have any reaction with the tissues inside. Otherwise, it will create chronic problem. So it has to be biocompatible. Packaging has to be biocompatible. The device should be able to survive. So biocompatibility is important for the implantable device. Very good. Anybody else? So I'm just,
There will
application point of view, wearable versus implantable. So somebody said this has to be biocompatible. Anything else?
power constraints will be there. Different power constraints for both the devices.
So what is the difference?
Like we can wearables can be like charged, like
Yes.
they can be chargeable, but the
Yeah.
implantable
So
device
power
is connected.
supply is a major challenge. So power supply, power constraint is going to be higher, or you can say power uh, constraint is going to be higher. Here it is lesser because if it is outside, you can anyway charge the device. Inside, there are ways in which it can be charged. Like, people have tried inductive charging where you put a inductive charging chip, uh, inductive power transfer, right? Just like these days you have wireless charging, inductive charging of the cell phone. You can keep it on a pad, charging pad, and it has a electromagnetic charging. There is a coil inside this. There is a coil in the mobile phone, and when there is energy radiated by this coil in the charger, it basically passes. It energizes the coil in the phone, and that way the phone gets charged. The energy in the second coil in the phone, it charges the battery. This is called inductive coupling, electromagnetic, coupling between the two inductors. One inductor in the charging pad, another inductor is in the phone, and you are energizing, you are supplying power. This one is plugged into the, AC. You have the, this uh, lower inductor plugged into the AC, and that is energizing the upper one. Same mechanism people have tried to do it for the implantable device. You put an inductive chip, so both the chips are having inductors. Outside, you are able to pass the power wirelessly into the implantable device, and that's how it can survive. Otherwise, replacing battery is not feasible. You have to keep doing the surgery. So it may not be possible to, rely on a single battery for the device for a long time. So the power challenges are going to be much more uh, stringent. What else?
The implantable device needs to be smaller as compared to the wearable device because the implantable device is going inside the brain.
Yes. So I should rather say, yeah, the area has to be smaller, compact, more compact, smaller, or you can say area constraint is a bit higher. What else? So because form factor is important, implantable devices you may have serious form constraint. The area is very constrained. Chip size has to be small. Package size has to be small. Uh, Wearable device, you are more relaxed because it can be outside, so lesser. So if you're going inside the skull, then the chip has to be very thin. Package has to be very thin. Chip is anyway very thin, but the package has to be very thin so that it is fitting within the skull, a gap between the skull and the brain. So in that case, it is something like it's not only the chip design problem, but the packaging problem also. This biocompatibility also packaging problem, more of a packaging problem than the chip design problem. Anybody else? Power is a chip design problem.
The wearable device needs to be comfortable enough to wear. We need to design certain like wearable
That is
constraints on
okay.
it.
Outside devices, wearability, yeah, means as I told you, in this case, you may have a couple of options. First of all, it should be demonstrated scientifically by the biomedical group that yes, external device can do it. Externally, you can detect it also, and you can stimulate it also. Suppose it is done, I'm just assuming, right? Suppose externally also it is possible. So if it is possible, then you can design a chip which can sit outside and it can sense and it can stimulate. Stimulation part is going to be even more power hungry, right? Because stimulation sensing is requiring amplification of the signal that you are sensing in the neurons. Stimulation is you have to drive the brain region with electrical stimulus. And whenever you have to drive load, because in that part, in that case, the chip is supposed to provide electrical charge pulses, current pulses to that part of the brain. It is going to be very power hungry. So sensing part going to be, I would say, less power hungry, but when you have to stimulate also, that is going to take good amount of power. Assuming that the stimulus is not very frequent, sensing is continuous. You're sensing all the time, but only when the seizure onset is detected, then only you are stimulating. So stimulation is less frequent. It is occasional only, but whenever it happens, it will drive good amount of power. It will it will require good amount of energy because you are having continuous electrical pulses being driven to that region of the brain. So that thing we will discuss later. Anything else? Power constraint is not only because of the battery operation. There is another reason. Anybody can guess? One is the power constraint because of battery, or basically you have to supply the power inside the chip. Outside it is anyway chargeable. Inside you have to rely on inductive coupling. Or if there is another implantable application where going deep inside the body, it becomes very difficult. You can't really charge it like this. If it is on the surface, near the surface, then this works. For brain implants or inside the skull, you are implanting the chip, then still it is possible. There are some, some implants which may be just below the skin. In those cases, it is possible. Otherwise, not. What else is the reason for the power constraint?
Power constraint, we cannot put a very high power chip inside the brain because then it will heat too much.
Yes, so heating is another problem. So because heating biological tissues will create long-term damage. So power is not only for the battery, but the heating constraint. You should not have too much heating. Even few degrees of temperature rise continuous, it will create problem. Long term, it will create problem. It may start damaging tissues. It may start changing the tissue structure in some part of the brain. So it should not be heating beyond a certain value. So there will be some stringent power constraint related to heating also. Anything else? Cost point of view, this is going to be much more costly. This is going to be much more costly as compared to this one. So cost is also going to be high overall because packaging and chip design, it has to be small. It has to be, low power. Packaging is also challenging. Overall, it is going to be a much more costlier solution as compared to wearable. So if somebody says that using wearable device, also this kind of sensing and control is possible, then we will definitely go with wearable devices. And the other thing is the risk, human, risk, that it has to be approved by the medical agency or whatever is the authoritative body in that country, so that it can be used by people. Because implantation, it has certain norms. Like in US, there is something called FDA. So you need to get approval from those agencies before you can use this. Wearable also you need some approval, but less risky. So risk involved is much more. So application point of view, this is the discussion, right? Okay, we have started with an application. So a biomedical engineer or a medical engineer told you that there is a requirement like this, phenomena has been shown, control, sensing and control is possible. Now, these are the two options. You have to tell us what you can give us. If you have to go for a wearable device, what kind of things you will need, what kind of design components you will need. So from all these that we have discussed on the above list, what are the things you're going to require? So the subjects that you have just now we have discussed, analog is required because any sensing, you will require analog because signal is analog. So you need to, capture that signal, sense that signal. So that happens in the analog domain. So you need analog. But you need to digitize that signal. After the sensing, you need to digitize that signal. So after the digitization, everything happens in the digital domain. So we need digital also. I will come to that point, why we go to digital domain, why not continue in analog domain. Some of you may know the answer, some of you may not. So we'll discuss that point as well. And then there is some, signal processing also involved, because ultimately the target is to detect the seizure. So definitely you need to process that signal, whatever you have recorded, digitized, you need to process the signal, right? So that you are able to detect the seizure onset reliably. You should not be giving false alarms, right? So the signal processing algorithm that you are developing or your friends are developing, it should be accurate enough. It should not give false alarms, or it should not miss the seizure. Something is called false positive. False positive means there is no seizure, but your algorithm is accidentally detecting seizure. That is false positive. And false negative means there was a seizure onset and the patient went into convulsions. He got a seizure, but your chip failed to detect it timely. So that is false negative. So the signal processing algorithm should be robust. It should be foolproof, and it should work under all conditions. It should be reliably able to detect the seizure. It should not fail. Signal processing is very critical. Ultimately, that signal processing is getting implemented in digital or analog domain. And for implementing signal processing, you need the programming, you need the signal processing code, you need the DSP code. And ultimately, that signal processing will be implemented in some DSP circuits, digital circuits, which are implementing the digital signal processing. That entire, that entire DSP may require filters. It may have feedback loops. The analog circuits may have feedback loops. So that entire stability control operation will come into picture. So you can see that all these things will eventually come into picture when you are designing this application, right? So starting from the application itself, we can see that there is a need for all these topics that you have covered in your theory class. Okay, any question before we proceed further? So I will take a small break. Let me just, there is some, and I will come back in 2 minutes. I'm just, there is no way to pause the recording, unfortunately. Either we have to stop the recording or we have to. There was an option of pausing, I remember, but I'm not able to locate it. In settings, anybody is aware? Is there any pausing option? Stop sharing. Full sound. There is no pausing option. So I'll take just a couple of minutes of break and I will be back. I can continue the recording also. So let me, how long have we recorded? Not much maybe. So let me just pause for some time. I will come back in 2 minutes. Okay, so I'm back. Let us continue. Let's. Okay, so application point of view, we had a brief overview. You need to first of all, before you start, working on the design of this, you need to understand the signal characteristics, frequency, content of the signal, amplitude of the signal. So basic operations like what is amplitude, peak to peak amplitude under normal condition, under seizure condition, what is the frequency content of the signal, all those things we need to understand. Uh, and how often does it come? You need to study the signal before we, implement the signal processing scheme and try to implement it on the circuits. So even before we come to this is an application specific design, right? So we are talking about an application specific design, and all the circuits included here for the analog part, digital part are dedicated to one particular task, one particular application. So this is in contrast with general purpose computing. For example, the computing that you are having in your mobile phone or laptop is a general purpose processor, which are doing many things, right? They are running many different applications. They are running, so many different activities. They are handling camera, audio, handling many different software application, Android application, RF communication, phone calls, video calls, everything is being handled. So there is a general purpose computing chip or processors, many different components of, that entire computing system is there. That is a general purpose computing platform. Whereas here we are talking about application specific. So in case your application is building a mobile phone, then you need to be, you need to include all those different components, all those different sub-component of the system, which is going to build that mobile phone. Mobile phone is also an application, but only thing is it is having a general purpose processing. It is having many more components, and each of them are serving, some of the other role. So starting from, application, next we go to uh, the architecture. So that is, what is the next step? So step B is the architecture. You decide about the hardware architecture. Why it is not able to. From application, we come to the system architecture. The system architecture point of view, we need to spell out, we need to decide about the overall system. What are the components of the system? So what are the essential building blocks of this system? The first part is definitely the analog interface. You can draw it like this. This is the analog front end, which is responsible for interfacing with that sensor, which is either sitting on the skull or inside. And this may involve an amplifier, filter, etc. Right? Amplifier, filters, etc. You may have a ADC, which is going to convert this analog signal, whatever you are getting here, into digital signals. So here you get digital output. And after that, this is in the analog domain. After that, you have the data, which is either going to store in memory. So you need a memory to store the data. You need a processing element. It may be a DSP, digital signal processing, which is going to process that data. You will need a communication unit, maybe, which is going to communicate that data. Because ultimately, it may be required to, you know, send an alert to your mobile phone also that, yeah, seizure has been detected and onset of the seizure has been detected. That depends on the application definition, because now today there are so many applications which are actually linked to mobile apps. So the especially for wearable devices, they may say that, okay, let us have an link to the mobile app also, so that you are able to communicate to the external world that yes, so many seizures have been detected this week, right? So you may have wireless communication. You have an RF communication, RF module. RF modem, which is having an antenna, which is going to wirelessly communicate the signal to your mobile phone outside. What else we are going to have? We will need a, we also need a driver, right? So we need a driver, which based on the detection, the DSP is going to tell the driver to stimulate the region, right? So this electrical stimulation that we talked about going to be driven by the driver. So this driver is supposed to provide that signal. So we'll need the driver also. To manage all this, we will need a power management system. Power management unit. In short, we can call it PMU. This PMU is going to, this is again a big block where it is supposed to manage the power of this entire chip. All these components are going to take some power because all the electronic devices run on power. So there has to be a power management unit, which is going to take energy from external source. It may be a battery, it may be a RF induction, inductive, whatever. Depending upon what, whether it is a variable or implantable, you will need a battery. Even if it is implantable, you will need a battery so that the energy is stored. You charge it once and then energy is stored. Ultimately, it will take power from some battery and it will supply power to all these blocks. So ultimately, it will supply power to all these, blocks. So different voltages may be required. For example, the driver may require large volt, maybe 5 volt. Maybe the ADC will require 1 volt. Maybe the memory will require 0.7 volt. Maybe the DSP will require 1.2 volt. Depending upon maybe this one will require 3 volt. So depending upon this one, the RF module may also require multiple voltages. It may require some internal modules, some internal circuits. It may require maybe 1 volt. Some circuit which are driving the antenna, it may require larger values, maybe even 3 volt, 4 volt, whatever. So again, this power management unit is supposed to take care of, it is supposed to supply power to all these modules, different levels as per the requirement of that circuit, and also take power from the battery. Even the battery charging has to be done. So if there is a battery outside, there is a battery sitting somewhere outside the chip, there is supposed to be charging of the battery. Even that charging process has to be controlled by the power management unit. So it is not a one-way traffic. The power management unit also needs to control the charging of the battery. The battery control is also responsibility of the power management unit. It takes power from the battery, distributes to other units, regulates the voltages, and it also takes care of the battery charging, the control of the battery charging. All these processes are controlled by power management unit. What else do we need? We will need a clock unit, clock generation. Because all the digital blocks, memory blocks, even ADC, the driver block, RF block, all of them will work with clock generation unit. All of them require clock generation unit. So is there any other color? Because I don't see any other color. Yeah, color is there. So so this clock generation block, likewise, it will produce on-chip clock and will send that clock to all these modules, DSP module, driver module, everywhere. Even the power management module will require clock. So again, this is also an important block because many modules, most of the modules will require clocks to operate. When you are doing digital processing, when you have covered the digital circuit course, you know that digital circuits, some of them are combinational, some of them are sequential, flip-flops, registers, counters, all of these require clock to work. All the sequential circuits require clock to work. And any digital system, digital architecture, digital module is a combination of sequential and digital circuit, sequential and combinational circuits. Therefore, clock is always required. Even memory is also going to run with a clock. And even the ADC, there will be ultimately for ADC, there is something called sampling that all of you have studied in your signals and systems, signals and networks, that before you convert the analog signal into digital, there is something called sampling. You have heard of the sampling theorem, the Nyquist criteria, right? So there also ultimately sampling will happen through the clock. So even before the signal comes to the ADC, there is a clock involved in sampling. And even I will not hesitate in drawing this to the AFE. Even the AFE, we will see that many analog front-end designs will have digitally driven circuits, clock-driven circuits, chopping amplifiers, which will require clock. So the clock is everywhere, it's required everywhere. So these are the blocks which are catering, enabling the functionality of other modules, power management unit, clock generation unit, they are enabling the operation of all other modules. So in this entire system, we have all these different modules required to complete that chip. The single chip is going to have all these different things. And in a prototype design, you can have a PCB, right? You can make a PCB and connect all these different chips and make a system. But in order to make it compact and a wearable device or an implantable device, this has to be an SoC. This has to be a system on chip. All this functionality should be integrated in a single piece of silicon, possibly. So it has to be on the same chip. And there are some more advanced techniques these days, like system in or chip in multiple dies being connected through silicon wafer. Those we will discuss later. But the first stage is that, means if you want more integration, more compact design, you get to a system on chip architecture where all these different modules are sitting on the same die, same chip. And you try to minimize the area, you try to minimize the design complexity. So generally, if you look at this entire system and so many different components, if you go to industry, within the system architecture, there will be people who will be specializing in all the different blocks. Some people will work only on ADC, some people will work only on power management unit, some people will work only on memory, some people will work on DSP, clock generation. So each of these modules, there may be dedicated groups in the company where people will be working. You may be able to switch the groups also. So today you are working on ADC for 2 years, 3 years. You want to get experience in DSP. Okay, so you can apply, and if you are having sufficient background and you have done some work at least, you can possibly become part of the DSP group tomorrow. Analog to analog shifting is more easy. For example, DSP guy can switch to memory because memory is more digital in nature. It has analog as well, but more digital in nature. Likewise, the ADC guy can shift more comfortably to maybe the RF module, RF IC design. The clock generation person can shift to, say, memory. Likewise, people keep changing group in industry also, but it is important to know that, means in a IC design company, you will find people working in different groups, which are dedicatedly working on one particular module. Many different applications will have different specification for each of these modules, right? For this application that we have started with, the ADC specification may be different. How many bits are required? What is the sampling rate required? What kind of noise we can tolerate and still give you good result? All those things are ADC characteristics. So how good and how robust an ADC you need, how costly an ADC you need, will depend upon the application. Likewise, the analog front-end specifications will depend upon the application. So this is the system architecture. From the application, we come down to the system. These are the things required, right? Anybody else? Anybody having question on at this point? Anybody having any question at this point? I hope you're able to hear me. Anybody? No questions? Then let us go forward.
Yes.
Going down. So this. So after we have discussed the system architecture, right? So architecture. Then we go to. This is a little bit annoying. Why isn't something is wait a minute. Okay. Something is hanging. Wait a minute. not letting me select the pen. Steam thing is a bit. First of all, this does not go. This control panel does not go, and then it is not letting me select the pen somehow. Wait a minute, so I have to minimize this. Somehow it is getting clamped and not letting me select the pen. You know what happened? Let me check what is wrong. So this is fine. I'm trying to select this, but this red thing is not going. Red thing. What is going on? We go up a little bit. Something has gone wrong. So if I go up, this thing is there, but now if I want to select anything, now it came. All right. So now once the system specification is uh, done, of course, I have not gone into the detail of the system specification. So based on the application, as I said, you will have to decide about the system level specification. Digital side as well as analog side, there will be several specifications for each of these blocks, right? The basic things that I told you, for example, just going back and talking about some specifications. So what are the, so continuing on the system part, I will come to the point 3 later. So let me delete this point 3. So at the system level itself, you may have some high level specification. So what are the specifications we are looking at? So each of these blocks will require certain specification. For example, the ASC will require the signal that it can handle, right? So what is the signal amplitude that it is going to happen to handle? So the amplifier gain, bandwidth, the noise, because each circuit component also contributes to noise. So how much noise is allowed, how much robust it should be, what should be the noise figure of the circuit. Those things we'll discuss subsequently, but these are important parts for the uh, analog front end side, right? The ADC will require the sampling rate. It will also require the digital, I would say, the resolution. It also has some other parameters like non-linearity. Those things we will discuss later. Right now, you may not be aware of those. So there are some parameters related to non-linearity, for example, because ideally we would like the ADC to be perfectly linear, but in real world it is not. It has some imperfections. So this non-linearity is measured in terms of INL, DNL, etc. There are some other parameters related to distortion in ADC. Dynamic parameters are there, SNDR, SFDR, but at least basic things are these. What else? So the power management unit will need to know the power source. What is the voltage of the power source voltage, output voltages, voltage levels, how many of them are there. What else? Tell me. What else the power PMU should know? The engineers who are going to work on the power management unit, that particular group, what all they will know, they need to know. Quickly, anybody? Yes, hello? Hello? Anybody can answer this? The PMU people, what they will need to know? Am I audible? No answer. Is it going over the top? Not clear. Power management unit. Some things I've already written.
State of charge
What else?
estimation.
People listening, or I'm just
Hello.
Hello? Something is hanging.
Hello.
So can you hear us?
Something is
Hello?
hanging.
Hello?
Hello.
So you people are able to hear me? Hello? Yes, so please answer. So somebody's saying you can't hear us. So all right. So my audio is on. Now my audio is on. I think somehow I had switched off the audio. Now you tell us in the answer.
Individual power requirements of the different components that are there.
Okay, so this one goes. This also goes. So output voltage levels, and somebody said power requirement, power consumption of different modules. Anything else? Anything else?
If you are using a battery, then it might need to it might need to know the charge of the battery, the remaining charge in the battery.
That is, power source. It has everything like the output level of the battery and total capacity of the battery, the charging, discharging characteristics of the battery. Everything comes in the power source. So entire information about the power, the battery itself has several parameters: the charge rate, discharge rate, and this is the charging characteristics of the battery. It has total capacity of the battery, how much maximum current it can deliver to the chip. All those things are also characteristics of the battery, so that it needs to know. The power source I have taken it a single term, but it has several sub parameters of the battery also. What else? Any other thoughts? I am being a little bit careless about my handwriting. I hope it is readable to everyone. In case you feel it is too bad, then I will try to improve a bit, because on writing pad, generally, digital writing, it is a little bit difficult to control the handwriting perfectly. But in case you feel that it is becoming unreadable or too dirty, I will try to control it better. Yes. Anything else? So there are other, there are many other um, things. One of the main is supply noise, supply ripple. Or noise.
Sir, one thing is that like how much power supply rejection ratio.
Power supply, somebody
Like,
already mentioned power consumption of module. Then power
sir,
consumption of the
I'm
module
talking
means
about I'm talking about power supply rejection ratio, like that. Like when you the main power source, it may cause it may lead to some signal, right? So it may cause some input signal
yeah.
to
So
the
that's what I'm mentioning, the supply noise or ripple, right? So the so you have all these different modules, and they are working on the same chip, and they will lead to different current profiles. So assume that there is all these different modules, they will have their different current profiles. They will load the power management unit in a different way. Just like when the electricity is being supplied to a colony, somebody may be having a big family and they are having too much electricity consumption, too many refrigerators, ACs, and whatnot. If somebody is having a small room and not many people, they are not loading the electricity supply much. So in a electric supply line, you may have different kinds of loads. Just like that, in the chip also, different modules are there. Each of them have different kinds of power profile. The amount of current that they need will be different at different times. The kind of current profile they will need will be different at different times. So that current profile definitely, you may require peak peak current profile, peak current of different modules. Because some modules like the transmitter, the RF transmitter, when it is transmitting wirelessly, then it will require much more current. When it is not transmitting, only doing some processing or sleeping mode, it will not require that much current. Likewise, memory, when you are reading and writing into the memory, it will require some more power. When the memory is just storing the data, not reading, writing, it will require less power. Likewise, in any modules, like you may have some applications, some conditions under which the module will drive more current. In certain case, will less. Like the driver module, anyway, all the time it will be sleeping. Only in certain condition it will be activated. So the peak current profile of different modules will be different. That also we need to know. So all these things I need to know. I'm just giving you an example. What else? So this one is power, the supply noise of the blocks. The supply noise, why is it important? So the power management unit is supposed to uh, supply the power level to all these blocks. Where is the eraser? Eraser. I thought this is the eraser, but is the eraser is not the eraser. Where is the eraser? Oh, this is the problem. There are supposed to be an eraser here, but somehow raw. Where is the eraser? This tool is coming from somewhere else or what? This is the tool, but I'm not able to locate the eraser. Well, raw settings. This is MS Teams annotation, but somehow it is not able to access the drop. This is the MS Teams, but it is not letting me access the panel of the application, which is strange. So somehow this is linked with the MS Teams application. It is letting me annotate with all these colors, but the OneNote application it is not able to access any of the eraser or pen, etc. So MS Team has taken over the screen. MS so that is a problem because it seems like they don't have a clear all annotations. So this is annotations. This will create problem because while saving, I need to make sure that they are able to save. Otherwise, because I don't need this MS Team annotation, I need to turn it off. Let me turn it off. Only I can forget about this, so I can just remove this. Because I don't want the MS Team to control the annotation. I need the drawing panel here because otherwise it may not be even saved. So I need to just figure out what has happened. So just a minute. So yeah, first day sometimes we get all these setup issues. I need to get this control out of MS Team so that I can access the panel here. Draw. Got it. So this is the eraser. Now it is coming. Okay, so coming back. So I mentioned supply noise because once again, your supply noise specification for different blocks will be different. Like the analog blocks, amplifier, etc. You will require a supply noise maybe less than 1 millivolt. The supply noise should be less than fraction of millivolt because you are sensing very small signals. You are sensing maybe 0.1 millivolt of signal. And then if the supply noise itself is several millivolts, you will not be able to sense. So the analog front-end side, the supply noise must be very, very less. Digital side, the supply noise may be, bigger because digital circuits operate with 0 and 1, 0 and VDD. So there, even if 100 millivolt of supply happens, it is okay. So the output which is going to the digital block, the supply which is going to the digital block here, this particular line, memory and DSP, wherever it is going, those voltages can be allowed to be a bit more noisy. I don't need to make them very, very precise, very, very clean. But the voltages which are going to ADC, analog front end, those need to be a lot more precise, very clean, less than fraction of millivolt noise. So all those specifications for different blocks we need to know. And again, how clean the supply needs to be, that depends upon the circuit of the analog front end also. Its own power rejection, so the power supply noise rejection ratio also. So all these things will depend upon the analog front ends, how robustly it is designed and how much noise it can handle, and also what is the minimum signal amplitude it is supposed to sense. If the signal amplitude is very small, 10 microvolt, then the power constraint, or I would say the power supply constraint, will be even more stringent. The supply needs to be much more clean. Some special power management technique has to be used. Anything else for the PMU unit that you get in mind? So roughly, we can understand that for each module, processor like specifications like this will be needed. You have memory. So memory, what are the specifications? We will ask anybody. Basic specifications. Yes. Anyone? Basic specification.
So,
What?
so the memory would need to be large enough for us to store the value. So for the different values that you want to store, like you want the different values you want to calculate on.
Yes. So capacity, right? So basic thing is capacity. Whether you need a few kilobytes or you need megabytes, it depends upon what. So this memory will depend upon how requirement of memory will depend upon what size of the memory, right? So it can range from few kilobytes all the way to very large values also. So what does capacity depend upon? Anybody? Rough idea on what this answer depends upon?
Capacity would mostly depend just upon the requirement that we have.
That we
How
know,
much?
but what is the requirement dependent upon? From where the requirement is coming? Which things will
The
tell you
type
that
of
capacity of the memory
processing,
required?
the type of
There's
processing
the
that we are planning to
number
do.
of bits, the resolution of the ADC, that the number of bits it will store will also determine uh, the memory
Okay,
capacity.
so that
Resolution.
is one partial answer. Maybe it will partially depend upon that. The ADC resolution, how many bits, etc. you are using partially. What else?
Yeah, we would need two kind of memory, the static and the dynamic one. So the dynamic
Why?
one would depend upon the kind of processing that we are doing with the amount the data stored that we have.
Okay, so what is it dependent upon? So you almost got there. So what will this capacity depend upon? Strongly. It will
Processing that
depend
we are doing.
upon what?
The processing that we are doing, the kind of processing.
Processing, yes, algorithm. So whatever is your signal processing algorithm, it will heavily depend upon that. So the signal processing algorithm is such that it requires storing of huge amount of data, processing, storing some intermediate results. So it will require more memory. So there are many signal processing algorithms that you may have seen, like FFT or Fourier transform, discrete Fourier transform, some filtering, low pass filtering, high pass filtering, band pass filtering. All of these, some averaging operation. So all of these will require some memory. So depending upon what kind of processing you are doing, you need some memory, right? So for example, if you have simple averaging, right? Averaging of 100 samples. So you need to store those 100 samples, right? Then only you will be able to take the average. So you need to have all those, memory requirement based on the algorithm that you are choosing. What else? You may have another thing, access speed, how fast you are able to read and write. Power consumption may not be so important because power of memory will be less than others, but main thing is the capacity in this case. Access speed may be important, but in this case, biomedical signal generally, the access speed may not be so high, especially if it is a one-dimensional signal. Uh, so access speed will be lesser important. Capacity is the main thing. Anything else? So even I can ask similar question regarding this thing, ADC, sampling rate, resolution. For ADC, who will decide the resolution? How will you know what is the resolution requirement? If you have read some of those lectures, I think you may have the answer. What will be the ADC resolution depend upon? Who will tell you what is the ADC resolution required? Resolution, you understand, right? How many bits? So
Like the
each,
DSP block, how I implement the DSP block and like the signal amplitude of the signal, how much it's varying. Will
yes. So
tell
again, that
me
also
that.
depends upon signal processing. So if your signal processing algorithm, the one person who is working on signal processing algorithm, he says that my algorithms will work only if the data is precisely digitized. I need 24-bit data. Then you need a 24-bit ADC, which is a lot more complicated as compared to 8-bit ADC, right? So that depends upon the signal processing person who is developing the algorithm for the seizure detection. If he says that I can do it without digitization also, or I can do it with 4-bit ADC, I don't need very high precision ADC, then the ADC design is simplified. So that is strongly dependent upon the signal processing once again. So what kind of signal processing is being done, and the signal processing person himself, herself, he will decide. They will analyze the algorithm with different data precision, and they can tell you that what is the precision required. Based on that, you design the ADC. So this requirement of sampling rate, resolution, how much distortion, this nonlinearity, etc., they can handle. That will come from the algorithm person. Like how much sampling rate is required, who will tell you? Again, signal processing side, because they know the frequency content of the signal and how much signal frequency content is useful. For example, the signal may be having frequency content a pretty what is happening. Signal may be having a pretty wide frequency content from 0 hertz all the way to kilohertz, something, several kilo or 100 kilohertz. So now it's necessary to find out that which part is important, right? So it's possible that this entire spectrum 0 to 100 kilohertz is not important. Some analysis in the signal processing tells us that only from 100 hertz or 1001 kilohertz to 100 kilohertz is required. Then you can discard this part. Then I can filter out. I can filter out this information, and I need to process only this information. So that will tell us about the bandwidth, about the sampling rate, because ultimately frequency content of the signal tells us about all this. So again, all these specifications regarding bandwidth, sampling rate, how much noise we can handle, that can be assessed by the signal processing team. Anything else? Yeah. So likewise, I'm just talking about some of these. Like the clock management unit, or the clock generation unit, clock gen, that will also, the main specification there is what? What is the main specification? Clock frequency required, right? There will be different blocks which are operating with different frequencies, and it is supposed to provide that frequency to different blocks, or it is supposed to provide the highest frequency from outside. It will generate the highest frequency required for operation, and different blocks can divide the frequency and take the whatever frequency is required. So that clock frequency requirement, the highest clock frequency requirement, that has to be decided. What is? So we have the RF module also. So the RF module, once again, it will depend upon the power to be transmitted, right? So output power is a major criteria here, because ultimately how you are transmitting and to what device you are transmitting, it will depend upon that. If it is only for a nearby device, it may have to transmit lower power, assuming that it is only covering 1 meter radius around your body, then the power for the transmission will be lesser. If it is supposed to transmit much longer, then it has to be more power. So that is going to be an important parameter, because RF modules are power hungry, and the maximum power goes in driving the antenna. So that part we have to decide. And other things like the modulation schemes, what kind of modulation you will be using, what kind of communication scheme you will be using, whether it's going to be a frequency modulation, whether it is going to be CDMA technique, whether it is going to be some other modulation techniques, depending upon the data rate, how much data rate you need, all those things, even data rate is important, like the RF data rate, right? So whether you want to transmit much faster or you want to transmit uh, only small amount of data, that will also depend upon the data rate, right? So one possibility is that you transmit the raw data, right? So the entire raw data that you are receiving all the time from different sensors, you transmit this entire thing to outside chip and send it to the mobile phone, right? And run your DSP algorithm in the mobile phone. This is your mobile. So one extreme case is you don't do any DSP on the chip. You just record the data, digitize the data, and use the RF modules, send it to the mobile, and rest of the DSP happens here, right? That is possible. But then the RF module will have to consume good amount of power because it is transmitting all the data to the DSP. So now the decision is that if whether this is a more efficient scheme or putting the DSP on the chip is more efficient. So that decision, who will tell us? We have to decide, we have to estimate that in one case, I am putting the DSP on the chip and doing the processing right there and getting the results of seizure detection, right? So there, on the chip itself, I'm able to detect that seizure, and then I have to transmit only small amount of data. Only an alert has to be transmitted. That when the seizure is detected, you turn on an alert signal, and that goes to the mobile phone. The person is alerted that yes, there was a seizure detected, and stimulation has happened, and you have been saved from the seizure. So in that case, I need to transmit only few bytes or few bits of data. That's all. But if it is the raw data, I will transmit all the time. This RF transmitter has to be active all the time. It will consume huge amount of power, right? So therefore, this application, it may be better. Somebody is asking anything. So in this application, it may be better to do the chip, do the processing on chip. Let the DSP operate on the chip itself and communicate only the result to the mobile phone, so that the RF communication power, the wireless transmission power, is saved. You are transmitting only when the detection has happened. In that case, of course, logically, you have to make sure that whatever you are spending in the DSP, the entire DSP that you're doing on the chip, that power should not be too high. If that is true, if the DSP power is not too high, it is only a very small fraction of the RF transmitter power, then you have a rationale. Then you can justify putting the DSP on the chip. So whether to put the DSP on the chip or not, it will depend upon your DSP algorithm. If you are able to simplify the DSP algorithm and have a smart algorithm which does not require too complicated processing, it does not require too much of computing, but it easily gives you the result with minimal processing, then the power consumption of the DSP will be less, it will be limited. Then you can justify putting it on the chip. But some computer science guy has come up with an algorithm, and without understanding the hardware constraint, his algorithm is requiring too much of processing power, too much of memory. In that case, it will end up burning too much power for the computing. It will require too much memory for the computing. So then it will not be suitable for deployment on the chip. So if you have to save this RF power and justify putting DSP on the chip, it has to be a simplified or low power DSP algorithm. Compute effort has to be less. It has to be relatively lightweight DSP algorithm. Likewise, it also has to require less memory. If the DSP algorithm you have designed is too memory hungry, it is requiring too frequent memory accesses, or it requires too much of memory, that will also be disadvantages. So the DSP algorithm has to be optimized. It should work with relatively low precision data. It should be able to work with relatively, maybe lesser sampling rate, or it should not require very high speed processing. It should be able to, with relatively simpler signal transformation approaches, it should be able to give you the result. So those things need to be optimized before we can take a decision whether to put the DSP on the chip. DSP power becomes less, if it becomes comparable as compared to the RF transmitter, then you are losing the case. Right? What else? So from the system level definition, we are seeing that these are so many high-level specification that we can arrive at. I have not included generally there will be a controller, microcontroller unit also I can add to it. I have not included it because in certain cases you may club it with the DSP. So I'm just putting it as a separate unit, MCU. MCU is a microcontroller unit which will be having the program. So you can program it, and ultimately it is going to control the execution of all the other modules. So generally, the microprocessor unit, it will be, I would say, off the shelf because there are some standard microprocessor modules available. You can rely on those. So in the overall system on chip, there will be a microcontroller unit which is supposed to, it is going to have the program for the execution of the entire system. So when you program a chip, if you program an application chip, it will be ultimately programming the microcontroller unit. It will be storing the load instructions or program instructions in the memory of the microprocessor unit. So it may have either a program memory associated here, the program memory, data memory. So the program memory will be related to the microcontroller, and this microcontroller will be providing control signal to all these blocks, all these blocks. So it will be providing control signal to all the blocks. So going forward, so now we know the system level specifications and all. The next part is the blocks and circuits, right? So ultimately, once the modules are ready, we need to design the blocks. Specifications have been obtained. So we need to design these blocks, and each blocks will have different circuit components. So I need to design all these circuits. It may be digital, it may be analog, it may be RF components like the RF transmitter receiver. It may be, some high voltage devices for the power management. So again, all these blocks, circuits need to be designed. At the lower level, at the lowest level, we need to be aware of the device and technology. Device and the semiconductor technology. Because ultimately these devices are being used for designing the circuit. So memory side, you may have a different kind of device, right? The memory device may be slightly different. You may have to use certain special MOSFET which are suitable for memory operation. For analog operation, you may have to use different kinds of MOSFET which have lower noise. For power management, you may have to use another kind of MOSFET which is able to handle higher voltages, high voltage MOSFET. Likewise, for DSP, you may have to use low power MOSFETs or low voltage MOSFET, because generally DSP may be able to operate at lower voltages. So you may have to use low VT MOSFETs. So different modules will use different MOSFET, different kinds of MOSFETs. A single technology, a single foundry will provide different MOSFETs. For example, if you are going for a particular foundry, say TSMC, which is one of the biggest foundry or the biggest foundry, I would say, TSMC. So this foundry will give you different technology nodes. We will discuss about all these different technology nodes and scaling, etc. So suppose you're working on 65 nanometer TSMC. So for 65 nanometer TSMC, the MOSFET channel length is 65 nanometer. But it's not that all the MOSFETs in 65 nanometer are exactly same. There are different kinds of MOSFETs in 65 nanometer TSMC node. Some of them will be high voltage, some of them will be low voltage, high VT, low VT, higher oxide thickness, lower oxide thickness. Some of them can be suitable for memory, some of them suitable for DSP, some suitable for analog, some suitable for power management. There are different devices that we need to be generally aware of. So at the lowest level, these are the devices. There will be resistors, capacitors. Some capacitors will be more accurate. Some other capacitors will have more variations. Resistors will be there of different kinds. Some resistors will have more resistivity. Some resistors will have lesser resistivity. Some resistors will be more having more variations. So all these device information we should have, especially for analog engineers, it is all the more important. Digital engineers also require. So in the design hierarchy, we see starting from application, going to the architecture, going to the blocks and circuits, and then finally coming to the device, and semiconductor technology. So all this is the design hierarchy of the semiconductor chip. So we need to be, starting from application, we need to go down, and we need to design these circuits and blocks, keeping in mind the higher level specification and also keeping in mind the kind of devices that we are going to need for different applications. In the course, whatever simulations we do, that may be from some free source or open source model, which are done for academic purposes. So there we will not have all these different options for choosing devices. But when you, those of you who get interested in working in real projects, there we will be giving you access to industry technology and some industry standard design tools through which you can access the actual foundry devices for different nodes. If you're working on 65 nanometer, you will get access to the 65 nanometer TSMC devices. If you work on 22 nanometer, you will get access to that device model of 22 nanometer. Working on 10 nanometer, you will get access to that. Depending on what application you're working on and what node, you will get that kind of device model. But in the course, what a simulation we do, that will be using some open source device models, which are used for academic purposes. You can simulate some circuits in LT-SPICE, learn a lot of things, but they are for academic purposes. They are not industry device models. Any question before we proceed further? So two things we saw. One thing is the design hierarchy. That means starting from application, algorithm, architecture, blocks and circuits, and then devices. So algorithm part, I think I somehow did I mention the algorithm explicitly? System architecture. So yeah, I mean before coming to the architecture, I could have put another point here, algorithm, which is I would say part of the application, because we need to be careful. We need to know the algorithm, right? Whatever algorithms you are having, whatever processing you are doing, whatever signal processing is required, all that has to be clear before we think about a system architecture. So application is fine, but in that application, we should know the detail of the algorithm, that what data processing you are going to do. Because all the electronics that we are designing, it is targeted towards this algorithm. Whatever data processing, whatever signal processing you are going to do, we have to design the circuits for that. Therefore, the application, first of all, should tell us about the algorithm. So I missed writing algorithm separately, but after application, we have algorithm. Then based on the algorithm, we decide the system architecture. In that system architecture, we identify so many blocks. We decide the specification of those blocks and then design the circuit for those blocks. They based on those specifications. They should meet that specification. And then going back down, to design those blocks, we need to be a little bit aware of the devices and circuits, the individual device components, MOSFETs, passive components like resistor, capacitor, diode, whatever is required on the chip. Any question before we proceed further? Any question before we proceed further? Okay. So we can try to address some more points. You people, any doubt you should ask without hesitation. Any problem, anything not clear, not agreeable. I hope the recording is going on, I guess, right? Yes. So the one question that I asked you in the beginning, why are we going for digitization? Why ADC and after that everything in digital? So who can answer that? By now you might have already got the answer if you have seen my lecture somewhere, or if you, maybe in your courses, earlier courses also, basic electronics, introduction to electronics, you might have seen those. So, what is this analog versus digital thing? Why are we, digitizing? Why not keep doing things in analog domain? Who can answer? After covering analog circuits and digital circuits, you should know the answer, at least to some extent.
It's much easier to process digital signals.
What do you mean easier? So this is a vague answer. You need to say why it is easier. You are maybe having that answer in the mind, but you need to qualify why it is easier to process signals in digital domain. Why do you claim so? Yes. Why do you claim so quickly? When there are multiple answers, you might have already seen these answers in your courses.
Digital signals are like less susceptible to noise.
Less sensitive to
And
noise. So
yes,
why less sensitive to noise? I've already given that answer in the lecture earlier.
they have a
Mm.
they have a fixed high and a fixed low value. So like in an analog signal, when a signal comes in and if there is noise, the signal value, since like it can have any value between 0 to say 5 volts. So the noise can affect it a lot. If in a digital signal,
Yes.
low is
So
defined as below 0.7 or a high and a high is above
okay.
3.5. So like that can be maintained.
So analog, the noise sensitivity is going to be very high. Digital is low because digital works with 0 and VDD levels. Analog can have very small levels. It can be millivolt, it can be microvolt, and small amount of noise can corrupt your signal. So it is going to be very sensitive to noise. So the circuits in analog domain are very sensitive to noise. Supply voltage must be very clean. Circuits should not contribute thermal noise or other kind of noises to the signal. So noise point of view, analog is much more sensitive. Anything else? Yes, anything
Storage
else?
efficiency.
Storage. Okay. So this is difficult because analog, how you store analog data? How can you store analog signal? Why I'm calling it is difficult? Can't you store analog signal? How do you store? Yes. How do
There
you
is
store analog signal?
there is no proper mechanism to store analog signal.
What do you mean? You can't store an analog signal.
Since we have since the voltage levels on analog signal is always varying, we need to have some sort of mechanism involving a capacitor type of, which can always like store the voltage. But since there is no ideal capacitor sort, it will always keep on leaking and storage
It will
will
always
not
keep
be.
on what?
So the charge will keep on leaking, right? Means the capacitor will keep
Yes.
on discharging.
Yes. So ideally, a capacitor, even an ideal capacitor, you can put a switch on a capacitor, and whatever signal you are getting, if you turn on the switch at this point and close it, suppose this value, it will store that value, whatever this value is. Suppose 0.3 volt, you will get 0.3 volt here. Now, assuming that the switch is ideal and the capacitor is ideal, it will keep storing that voltage infinitely. But again, the problem is that no capacitor is ideal. Capacitors have leakage, right? And it depends upon how big the capacitor is. So ultimately, over a period of time, depending upon how much leakage the capacitor is having, how much is oxide thickness, it will ultimately leak that voltage. It will leak the charge stored, and it will distort the voltage. It will go to zero if you leave it for long enough time. And generally, capacitors are area consuming. So on the chip, if you want to place a lot of capacitors, it will take huge amount of area because they are parallel plate capacitor. You need metal area. Metal is later metal. That's how they are made. You can use MOS capacitor also, but ultimately structure is similar. You have so they will take good amount of area for the storage. So area point of view very inefficient, and leakage is also make problem. So area as well as current leakage. So area and leakage. Both these things will kill the analog storage. That's why storage is difficult. Whereas in digital domain, it is easy. Yes, so all the memories, whether it is DRAM, SRAM, even the solid state, SDRAM, all these are digital. They are storing digital data because digital data is 0 and 1, and they can be stored in certain digital circuits like SRAM cells or DRAM cells, or there are DRAM is also again capacitor based. So this capacitor storage mechanism is used in DRAMs, but again, it is not a stable, means you can't keep it infinitely. Ultimately, you have to refresh it. So in DRAM, there are ways in which the data is refreshed all the time. You sense it and write it back, sense it and write it back, so that data is not lost. So periodically, all the data stored in DRAM is refreshed. So we will discuss about all these different kinds of memories, but ultimately, all the data that we are storing is in DRAM. And why, analog versus digital, although DRAM is also capacitor based. So DRAM data is stored on a capacitor only. It is the memory of the DRAM is just like this, switch and a capacitor, and you have an array of capacitor. But why I'm saying it is easier as compared to storing analog? Because in DRAM, yes, any answer? The DRAM is a kind of memory which is having array of capacitors only, capacitor and switch, just like I've drawn here. But I'm saying it is still acceptable to store the digital data, but not analog. Why?
Since the digital data has only two values, 0 and 1, so
Yes, 0
like,
and 1.
until it
So,
falls below the
yeah, so the midpoint up to is close to, say, if it, as long as it's higher than the mid value, roughly, we can still identify it as 1. So starting with charge to VDD, and after some time it is leaking, it came down to although VDD by 2. Before that you refresh it, right? Then you are okay. But analog value, you are concerned with exact level. If you have programmed it to 0.3, it should be at 0.3. It should not go here or there. Within some tolerance. So that's why analog storage will be very difficult. Digital storage on DRAM using the same mechanism is okay, acceptable. And there are other memories, SRAM, SDRAM. Those are also we're going to discuss step by step. But all these stored data in some sequential circuits, like flip-flop or latches, right? So you have studied latch flip-flops. Have you studied the SRAM cell also, bit cell of SRAM 60 at 6 transistor bit cell of SRAM? Anywhere?
Yes, sir.
yes, sir.
Both E and EC people have studied. So E people.
So we haven't studied.
So, okay, no worries, we will discuss. But 60 SRAM basic memory device, which is just like a latch. It is ultimately like a latch. So latches, at least you have studied. So latch, latch circuit you are aware of? Any NAND latch or NOR latch? Those things you have studied.
Yes, sir.
So those circuits are ultimately like memory, right? The NAND latch, if you disconnect it from the input, the inputs are set to 0, 0. It will retain whatever output was there, right? It will not discharge. So they are like memory. Whatever you set it to, it will remain to that. Either you set it to 0 or VDD, output will remain like that. So latches are example of memory. Ultimately, all these SRAM bit cell that we have are something like latches only. We will discuss that. So we know all of you have come across memories. You in the lab also you might have used some memories chips which are storing few bits of data. So all of them are, as long as VDD is applied to them, they are going to store the data. And there are some memories which are non-volatile memory, where you remove the VDD, then also it will store the data. So digital storage is very much possible and much more convenient. What else? Quickly, what else? Yes. Anybody else? Quickly. Couple of answers I'm waiting for. Nobody has any further answers? I'm waiting for two major answers. The biggest answer has not come yet. I think in some of my recordings, I might have given those kind of videos, but I'm not sure. At least one of the answers you are all aware. Noise is an external factor which creates problem. There is an internal factor also which creates problem for analog. Noise is internal also because device circuits have their own noises, but I'm calling it external because it is corrupting the signal. What other factor is there in analog circuit which can create problem for the signal? Which can
Digital signals are more synchronous as they have a clock. Analog signals are not that synchronous.
no synchronicity has nothing to do with. What else? Remember your feedback circuits Why do we use these feedback resistors, capacitors, minus R1 by R2 gain? Why do we do all that? Do you remember anything? Yes. Anybody? Do you remember that feedback, op-amp feedback? Why do you use those op-amp circuits? Quickly, these are basic things.
Isolation.
So, so the gain
Isolation.
it is dependent on. So the gain is dependent on process variation. Uh, so
Grain is dependent upon process variation. Okay. So basically, in an op-amp, for example, if you have a op-amp, I guess two-stage op-amp, I'm not sure whether you have covered, but ultimately the single-stage amplifier, common source amplifier, gain is something like GMRO, right? And GM as well as RO depends upon many device parameters and temperature also, right? Like mu n, CUX, W, L. So all these device parameters are going to vary from device to device. It is also going to vary over temperature. Likewise, RO also depends on lambda and ID. All these parameters vary a lot from device to device. So in your lab experiments also, you might have seen that the GMRO calculated by one of your friends will be different from what you have done. You have taken a MOSFET chip and you have characterized the MOSFET, but the GMRO you got is very different from somebody else. Same thing happens on the chip also. Different devices will have different, significantly different VTs and, lambda. So the parameters will be different. As a result, the gain will vary. The GMRO gain, open loop gain of the amplifier will vary a lot. And as a result, you can't rely on this open loop gain. Also, another assumption that you take is the small signal operation. So this gain of GMRO is applicable for small signal, right? So there is assumption that the signal is much smaller and we are linearizing. So this entire small signal thing is obtained by some assumption that if this is the ID VGS characteristics, we are biasing the amplifier at a particular point, and then it is going to operate in this small segment, linear segment, and therefore it is going to be linear. But actually, once you go for larger signal, you will cross this linear region. You will go into non-linear regime, right? So ultimately, it will be you will be operating all throughout for bigger signals. So as your signal becomes bigger and bigger, your characteristics become more and more non-linear. This small signal assumption does not hold. So again, so the moment your signals are becoming larger, you will get more and more distortion. So this non-linearity and distortion will become a major problem. So for initial small signals, it is okay, but the moment you are having bigger signals, you will be having a lot of problem with the distortion. So this non-linearity and distortion is very prominent in analog domain because of the inherent characteristic of the devices. In digital domain, once you digitize it, is digital value that you can multiply, you can divide, you can add, you can do whatever you want to have. So these problems are not present. This problem not present, right? So this is a major reason why we'd like to convert the signal completely into digital domain and then do the rest of the processing in digital domain, because every analog stage will introduce its imperfections. Although an amplifier you may have designed using, this resistor feedback, we say that the gain of this is R2, R1, right? So this gain is minus R2 by R1, but it is only approximate expression. Real expression, it has the A naught, right? A naught is also involved, which is minus, R2 by R1 upon 1 plus A naught upon R2 by R1. So that A naught is also coming. So only in approximation, this A naught is much greater than 1 or much greater than your R2 by R1, then this approximation holds true. If the A naught is much greater than your closed loop gain R2 by R1 beta, 1 by 1 beta, A naught much greater than 1 upon beta, then only this expression holds true. Otherwise, you have to take into account the A naught. So all these are approximations that we do. And the more number of stages you have, each of these stages will introduce these non-idealities, and it will, introduce non-linearity in the signal and distort the signal. Whereas these things we don't need to worry about in the digital domain. What else? Still, the biggest factor is not discussed. Biggest. Yes. The biggest factor. Quickly tell me the biggest factor. Anybody? I'm waiting quickly. Nobody.
The power consumption, maybe.
Power consumption. I think somewhere in my recorded videos, I might have given these things. Power consumption. So power consumption, why is it different for the two cases? Why, analog is having a problem? All of you have studied CMOS logic. CMOS logic you have studied. EC people, E people, both of you have studied CMOS logic.
Yes, sir.
So you know that how different logic gates can be constructed using CMOS, right? Anyone quickly? NOT gate, NAND gate, NOR gate, how it is constructed using
Yes,
CMOS?
yes, sir.
All these are logic gates, right? All the arithmetic operation, logical operation, all the computation, digital domain, multiplier, adder, everything is based on gates. You can construct all these arithmetic units, logical units, flip-flops, everything is based on gates. The gates are based on CMOS logic, NAND gate, NOT gate, all of this you have studied. So how do we make a NOT gate in analog? Analog inverter, a simple single stage common source amplifier is the inverter, right? So you can operate this as an inverter. Apply VDD, output will be VDD minus I times R. If this is significantly large, it will go to 0, right? If the R is sufficiently large, go to 0. So the V high, if the VDD, if the gate voltage is 0, high will be, output will be VDD, because it will turn off the MOSFET, and there is no current flow, output will be VDD. V low, if the R is sufficiently large, it will VDD minus IR will be close to 0. So this is an inverter, right? But what is the problem with this inverter? Likewise, any gate, right? Any logic gate can be constructed using, this is the inverter. You can replace it with an inverter symbol. Fine. You want to construct a AND gate or NAND gate. Put these two devices A, B. This is R. This is the output. If your A and B both are VDD, both are turning on. R is sufficiently large. The output will be VDD minus IR, once again close to 0. And any one of them are low, the downward path is cut off, output will be VDD. So again, this is a NAND gate. You convert, you add these two, you get an AND gate. So this is the NAND. Likewise, all the logics you can construct using analog circuit. And there are many other arithmetic operations also you can do using analog, right? Op-amp, you want to do summation, you have the summing circuit. This is a summing circuit. V1, V2, V3. You can sum it up, no problem. You know that you have done this in your basic electronics course. So this is a summing circuit. You can even do multiplication, etc. Some analog circuits are there. It will not be very accurate. Non-linearity is there. We have seen just now, non-linearity is a major problem. But there are some multiplier circuits also where you can do small signal multiplication. But the multiplication operation is even more non-linear because you are multiplying two signals. Addition is still doable. So a lot of arithmetic operations, ultimately multiplier also involves, addition. So here also you can implement all these things, right? So multiplication, if you want to implement, that is also possible using capacitive circuits. But what is the problem? So just for the example of the inverter, I can show that here, if you are turning it high, means inverter, whenever the VDD gate is VDD, you are having a constant current flowing, ID always flowing. So there is a power consumption, ID times VDD. What is power consumption? You know, power consumption, what is the concept? How do we calculate the power consumption of this circuit? This circuit. Yes, what is power consumption of this circuit? How do we calculate? How do we define power consumption? So power
VDD into IT.
Yeah, so how does that come? Power is what? Power is rate of energy dissipation, rate of energy dissipation. So for this circuit, what is the energy dissipated? So if I look at this particular circuit that we just discussed, when the input is high, suppose 50% of the time input is high, VDD, rest of the time it is zero. So when the input is high, there is some ID flowing through it. So what is the power consumption during that time? We are talking about average energy dissipation. So when it is high, so what is the energy dissipation? How do we calculate energy dissipation? What is energy dissipation in this circuit? Yes, tell me, these are basic things. How does the energy dissipation takes place in the circuit? Ultimately, it is discharging your battery, right? So battery has energy.
So
It is
resistive
discharging.
power loss.
Yes, sorry,
Resistive power loss.
I didn't get it.
Resistor power loss.
Resistor power loss. No. I can remove the resistor. I can put it like this, VDD, still get the power loss. Why there is a power loss in this circuit? What is the main reason?
So this MOS will have some internal, some resistance across it. There is the R out. So some power energy will be dissipated across the MOS also. So to find the total energy dissipation, we need to find the total voltage across the entire circuit and the current passing. So V into
No.
I will give.
No. So you go to more fundamental reason for power dissipation. What is energy? I'm talking about, forget about power first, energy dissipation. This circuit is dissipating energy. Why it is dissipating energy? How is it dissipating energy? What is the reason for that energy dissipation?
So, electromagnetic waves also dissipate energy through.
Volume somehow is very low. Once again,
Sorry, current passing through it will create electromagnetic waves. Like we are switching it on and off and on and off. So that might.
electromagnetic waves. No, there is no electromagnetic wave here. What have you studied about the charge transfer? So if the charge Q is transferred from V1 to V2, does it change some energy or lose or gain some energy? So here electrons are flowing continuously, right? So it's positive charge in this direction, electrons are going in this direction. They are going from minus Q charge, n number of them are going from 0 to VDD, right? That means the electrons are losing energy. They are going from lower level to higher potential level. So when a negatively charged electron goes from lower potential to higher potential, it is losing energy, right? So the charge transfer is the major reason for energy dissipation. So the energy that is getting dissipated is because of the electrons getting transferred from a lower potential to higher electrostatic potential. And what is that charge? How much is that charge? The total amount of energy dissipation is the total magnitude of charge times the voltage across which that charge is transferred. That is the fundamental thing. So what is the charge over here? In a time t, the charge will be I times t, right? This is the charge in the time t, right? And the voltage across which the charge got transferred is times VDD. Therefore, the energy which is lost, delta E, in time t is this delta t. In delta t time, this much is the energy lost. And therefore, what is the power? the rate of dissipation of energy. Therefore, I times VDD is equal to delta E by delta T. This is the power. Therefore, power is power dissipated in the circuit, rate of energy dissipation, which is equal to I times VD. But now this is happening only 50% of the time because the input is high and low, high and low. So I can add a 0.5 times I times VDD. So on an average, this is the power consumption of this circuit. Likewise, many circuits, most of the analog circuits, amplifier, differential amplifier, common source amplifier, all the amplifier that you have seen, it will be having some static biasing current. All of them work with some biasing current because we are biasing the circuits at a high gain region, right? So we are choosing some bias point, and then this requires some, ID, some special ID for which it is biased. Therefore, all the circuits will consume that static power consumption all the time. This is called static power. Static because it's always that average current is always flowing, and as a result, that power dissipation is always happening. But when you come to digital inverter, they are not biased at a particular point, right? Digital CMOS inverter, NMOS, PMOS combination. So when this is high, which one is on? Quickly.
Then
So the lower one will be on.
Lower is on. So what is the condition? So what at the output, if nothing is connected, suppose there is no circuit connected, what can I assume the output to be?
0.
Sorry?
low.
0. Since it's shorted to the lower ends.
So ultimately, I can put a cap over here, right? C parasitic. If nothing is connected, then I can assume that there is a parasitic capacitance as connect because of the devices itself. This parasitic capacitance will come from the devices themselves. Effectively, I will have a load capacitance equal to the parasitic capacitances of the devices, right? That much all of you know. And then if the input is high, what is the state of the output?
Low. So because initially when the input was low, so some charge was stored across the capacitor. So now when the input will be high, so the lower NMOS will be on and the upper PMOS will be off. So the charge in the capacitor will discharge to the lower NMOS. So it will go to 0.
Yes.
The output will go
So now when you turn it on and assuming that NMOS is turning on, it will whatever PMOS is off in that case, right? So PMOS is off. You forget about the upper part. The NMOS will connect that capacitor to ground. So whatever charge is there, ultimately it will flow to ground and it will become equal to 0, right? Because this terminal is anyway 0, and you are connecting this terminal to ground via this NMOS. Therefore, it will finally discharge because NMOS will keep conducting current, right? VG is equal to VDD, which is greater than VT. So the gate voltage VGS is greater than VT all the time. So what is the NMOS current? VGS minus VT times VDS, right? So as long as this is anyway greater than VT, because this you have put it as VGS is VDD. This is VDD. This one you have already put it as VDD. Wait a minute.
So in the digital inverter case, then we'll have the power loss and the power gain only during the charging and discharging time of the capacitor, right? So for the remaining cases, there will be no power loss.
For which case?
Like we will have power loss in the circuit only when the capacitor is charging and discharging only for that time, right? For the remaining time, we won't have any power dissipation.
Yes. So
that will make my total power dissipation less, right? Because
yeah, that's what we are coming to that. First, I'm talking about some basic things. So here we're talking about the condition of the output node, right? So some people are not even able to answer what will happen to the output node when the input is high or low. What is the condition? So, I'm trying to explain that okay, how to arrive at the output, like how do you justify what is going to happen to the output node if the input is high? Input is high means VGS is VDD. The VGS is greater than VT. Therefore, initially the VDS can be anything, starting from VDD to ground, anything. So as long as the VDS is positive, what happens? As long as the VDS is positive, this equation will make sure that current is flowing, right? The NMOS is going to have current. So only when VDS becomes 0, then only the current stops That means till the capacitor is fully discharged, it will keep sinking the current. The moment it is discharged, VDS becomes 0, then the current stops. Under that condition, the NMOS is still on, but it is not sinking any current because output is already discharged. The drain voltage is already 0. PMOS is anyway off. This is clear that okay, when the input is high, the output will be discharged to ground, and PMOS will remain off, NMOS will remain on, right? When the opposite happens, input is low, what will happen? NMOS will be on, sorry, NMOS will be off, PMOS will be on, and then it will try to supply current because now the current through PMOS is VSG minus mod VT, right, of the PMOS times VSD. So as long as VSD is positive, that means source voltage is higher than the drain voltage, it will keep supplying current. It will stop only when, because the gate voltage anyway, you have put it to 0. So VSG is always VDD. So this is VDD and VSG minus mod VT is always high. Therefore, the current will go on flowing till what time? Till the source and drain becomes equal. That means the drain potential becomes equal to the VDD. So till that time, PMOS will keep charging, and keep pulling it up to the VDD. Only when it becomes VDD, then the current flow will stop. Right. So in the inverter operation, the current will be required only to charge and discharge the capacitor. Once it charges completely, then there is no longer any current flow. Right. That much we can understand. So as compared to the analog circuit, here in the digital circuit, power consumption is only coming from the charging and discharging of capacitor. So this type of power consumption is called dynamic power consumption. In analog, it is static power consumption, static power. Why? Because there is a static current path between VDD and ground. There is a static current path, Any circuit where there is a static current path always on, or majority of the time, it is on, there is going to be static power consumption because from VDD to ground, there is a direct current path. The current is continuously flowing from VDD to ground. The moment that happens in the circuit, it is having a static power. Whereas in the digital circuit, ideally, if the input signal is a perfect, square pulse, at no time PMOS and NMOS are together on. Either PMOS is on or NMOS is on. And when PMOS is on, it is charging the cap. When NMOS is on, it is discharging the cap. The current flows in PMOS only for charging the cap. Once it charges, VSD becomes 0, current stops. Likewise, when the NMOS is discharging the cap, till the point the cap voltage becomes 0. After that, VDS of the NMOS becomes 0, it stops the current. So the current is going to be only for charging and discharging the cap, not all the time. So this is a dynamic power. If you want to plot the current as a function of input, this is the input waveform. How will the current flow in the NMOS and PMOS? So the PMOS current, how will we draw? At what point you will get, in this case, the PMOS current? Quickly. This is the input. At what point PMOS current will come?
When the input is going down.
Yes, so when the input is going down, just before this point, what was the condition? The input was high, therefore the cap was 0 and the NMOS was on. But the moment you cross this point, falling edge of the input, the NMOS is getting off and PMOS is getting on and cap is 0. Therefore, now the PMOS will start charging the cap. But as soon as the cap reaches VDD, it will stop. So the PMOS current will come short duration at this point and then it will go to 0. Right? The moment the output becomes the output becomes high, like the output will follow the opposite, right? So it will come, and when the input becomes low, output will start charging and then reach VDD and then after that remain high. Till the next time input becomes high again, it will remain high. The moment input becomes high, again it will go low because NMOS will discharge. So if I want to plot the NMOS current, what will it look like? NMOS current will be in the green color, this one. So NMOS current, when the input is going high, just before this,
It will be in the right
The
images.
input was low. Like, as a result, the PMOS was on, capacitor was charged to VDD. Now the moment input becomes high, NMOS is turning on and it will discharge the capacitor. So at this point, the NMOS current will be coming, right? So NMOS current will come at the rising edge, PMOS current will come at the falling edge. Rest of the time, it will not be there. So average power consumption will be only because of this current spikes that you are getting. Whereas in case of the inverter, what was this analog inverter? What was the condition? In the case of the inverter, analog inverter, the current would be like this: low, zero, again zero. For this entire high duration, the current will flow, right? Average power consumption will be much higher. This is the reason why most of the circuits will be in digital domain. We try to minimize the use of analog circuits because otherwise we will not be able to integrate the billions of transistors and circuits on a single chip, because the power consumption will become too high. Is this clear to all of you? There are a few more points. The design effort. Design effort point of view, the analog design, it has very less automation. It requires a lot of manual effort. A lot of, intuition, manual effort. People have tried to automate analog designs. A lot of effort is going on, but still perfect automation for the entire analog design, very difficult. Whereas in digital design, this is analog. Digital design, still, to good extent, if you have a code, there are tools which can convert that code into a digital hardware, right? So it can be automated because it is algorithmic in nature, right? So we have an algorithm. Of course, if you are knowledgeable about the digital hardware, you can optimize it much more. If you rely on the automated synthesis, it may not be the most optimal one. You may still have manual intervention required, but digital design has been automated to a very large extent. With analog design, you still require every component, every transistor, every circuit. You have a lot of manual effort required. So digital design is, I would say, more automation oriented, whereas analog design, a lot more manual effort, intuition. So it requires a lot of engineering effort to make that analog design, because specifications are too many, right? Power, non-linearity, gain, bandwidth, your noise, your swing, input signal swing, your ICMR, all those related to input common mode range. There's so many parameters in the analog domain that make the design complicated, and we need to put a lot of manual effort to design every circuit, every block. It requires so many of trade-off. If you increase power, if you increase the gain, bandwidth will come down, power will increase. If you increase swing, it will create problem with the noise, maybe. Many, some distortions will come, non-linearity will come the moment you are trying to increase the swing. So parameters will have conflict with each other. So when you try to meet the specification, you have to have a balancing act. All these specifications with respect to gain, power, bandwidth, swing, noise, non-linearity, we need to juggle with them and fix them so that they are all close to the required values. That's why for every module, a lot of design effort is required, and that makes the analog design challenging. So, I hope you got a good overview of this entire analog versus digital episode. And before that, we discussed the application design, where we looked at the design hierarchy starting from application, going to algorithm, going to architecture, blocks and circuits, and then devices. And within the architecture, we saw that what are the building blocks, what are the different components of the VLSI system on chip, what are the components of SoC on chip that will be required to implement that design. So I hope this is a good start. Any question before we conclude today's session? Any question before we conclude today's session? 10 people have already left.
Hello.
Any problem in reading the writing, or any problem in listening, any audio problem, video problem, any problems with the writing? If you feel anything is not clear, yeah, means in case I'm dealing with more complicated circuits, I will make it more clear. Right now, the way I have drawn it many places, it is a little untidy because done a little bit casually. But if it comes to uh, real circuit discussion, I can be a bit more careful in drawing. That I can do. So I hope, in case I have to teach uh, an op-amp circuit where you have a lot of transistors and we need precise uh, notations, etc. There I can control my handwriting. So don't get very disappointed with my handwriting. Sometimes I draw things carelessly, but wherever required, I can be, I can manage. Let me test, right? So it's pretty manageable. Okay, any question before we conclude? No question. So many things have been covered, people don't have questions. This is the problem of this present generation,
Hello.
that they don't ask questions.
Hello.
Yes,
Sir, can you please share the slides first?
that I will share. This is the only question I was expecting. Any other question? People are happy the moment, just to come to the class, get the slides. But in the class, very few people have questions. So either the generation is too smart, they don't get doubts, or concepts are very clear, or I'm teaching so nicely that everything is clear. The possibility of the last one is not so high. But
Sir,
other
they
possibility
asked
is
you
that
actually.
other possibility is that it is so boring that they are fed up. All the possibilities are there. So I need to decide, what is the real reason.
So, hello.
Yes. Any other doubt, questions before we conclude?
Sir, hello.
Yes.
Sir, I asked that in the beginning of the class that in one of your lectures, you mentioned one thing that I to V converter. So can you, if possible, explain that in short? If
Today it will
possible.
be difficult because already too much time has gone. So we will do it tomorrow. Any other question?
Can the classes go hybrid from tomorrow? I can ask better questions if I'm there present.
I will try that. I mean, that hall, I will have to make sure that that screen is there and we are able to record the voice and video using MS Teams. So that I will check tomorrow. I will try to stick to this timing as much as possible. So I will try to see that online option, offline option tomorrow. Any other question? Okay, so I will make this thing, the video is anyway there. I will make these notes available. As I told you, yeah, means looking back at my notes, sometimes I realize that I really mess up my handwriting, but it's okay. At least readable. Yes. Any other question before we conclude? Last chance. Okay, so if you don't have any question, we will stop and we'll meet tomorrow. I will confirm the timing for tomorrow.
Thank you, sir.